In this video, I'm going to talk about implicit differentiation, which is our first application of the chain rule. So what I want to start with here is just an example. So let's say we want to solve the problem of finding, so let's find the tangent line to x squared plus y squared equal 1. So that's a circle in the plane. And we want to find the tangent line with slope 1. And I guess here I really should say find a tangent line, because there may be more than one. Okay, so let's find a tangent line to this. Now it's not a function, it's a relation, because if you were to draw this, y is not a function of x because it's multi-valued. So at any value of x, we have two possible values of y. And so we can't really say that y is a function of x, but when we do implicit differentiation, we're going to sort of cheat the system, and we're going to assume that it is, and we have to be a little bit careful about how we assume that it is. And in particular, if we end up finding, for example, that this is the point at which the tangent line has slope 1, then what we can think of right now is that we're just going to zoom in on a piece of the circle right there and hunt in that region. Now we don't know where that region is yet, or maybe we do. It should be somewhere around here or here, because that's where the slope is, in the range of 1. But without knowing in advance where it's going to end up being, what we're going to do is we're just going to assume, okay, there are points out there that have slope 1, and we're just going to look at a piece of the circle at a time. And when we do that, we no longer have the restriction that we have to think of y as being a multi-valued relation in terms of x. We can say, let's say that y is a function of x just on a piece of the circle. And then using that assumption, now we can use calculus. Because the problem with a relation is that calculus, we take derivatives of functions, and if we don't have a function, then we don't have the sort of machinery that we usually use for differentiation. Okay, so what that means is that we're going to rewrite our x squared plus y squared as x squared plus y of x squared equal 1. Now you can explicitly write this, or you can just implicitly remember that you're assuming y is a function of x. And now we have a function of x on this side and a function of x, a very simple function of x on this side. They're equal according to the relation, which is what gives us the circle. But what we're going to do now is we're going to take a derivative of both sides of the equation with respect to x. And when we do that, we should still get equality between the two sides, because if two functions are equal, their derivatives should be equal. Now, if two derivatives of functions are equal, that doesn't necessarily mean the functions are equal. They could differ by a constant. But when you take a derivative, this is okay. So let me put that in brackets just to make it clear. So now we're taking a derivative with respect to x. So the first term just comes out as 2x, and the second one ends up as 2y of x. But then because there's something squared is an outer function and y of x is an inner function, we necessarily have to now do the chain rule, where we've taken the derivative of the outer function, which is y squared, but then inside y is actually a function of x, so we have to multiply by y prime of x. And that is the chain rule, right? This is like df dy of g of x, and then we multiply that by dg dx. Okay, so let me just erase that so I can write some other things below. And on the other side, the derivative of 1 is, it's a constant function, so its derivative is just 0. Okay, so now we have a constraint in the problem, right? We're asked to find a tangent line that has slope 1, which means this number here, y prime, we're looking for the x values at which y prime is 1. And so we could solve for y prime directly. So we could write down y prime equal a bunch of stuff. But we can also just say, well, I want to plug in 1 here and then figure out what x and y values will give me that. Okay, so I'll do that. And And so I get 2x plus 2y of x times 1 is equal to 0. And so if I solve, I get 2y of x equal minus 2x, and then divide by 2. So we have y of x is equal to minus x. The 2's cancel. Okay, so that means that the x and y coordinate have the same size but opposite sign. Okay, that means they are, well, they have to be somewhere along the line y equal minus x. So if I put that in, and there's two places where the line y equal minus x intersects the circle. One is here and one is here. We can actually plug in this y equal minus x into the equation above and solve for it. So we get x squared plus minus x squared equal 1. And so that tells us that 2x squared is equal to 1. And so x squared is equal to 1/2. And x is therefore plus or minus 1 over square root 2. Okay, so now we know the x coordinate. For each of those x coordinates, we'll have a y coordinate. And so what are the y coordinates then? So if x is equal to 1 over root 2, then y is equal to minus 1 over root 2. So that's 1 point. And if x is equal to minus 1 over root 2, then y is equal to plus 1 over root 2. And the other point is minus 1 over root 2, comma 1 over root 2. Okay, so now we have found 2 points at which the slope is minus 1, and they are right here. Okay, so now we have to find the tangent line. So we put it into, let's say we're going to choose just this one down here. So that's the positive x value and the negative y value. So if we want to put that into form of a line, we would have y equal mx minus x naught plus y naught. And when we replace the pieces, we know the slope is 1 because we forced it to be that. So I'll just leave that out. I'll just leave it as an invisible multiplier in front, and then x is going to have the x coordinate up here subtracted from it, and that is minus 1 over square root 2. And then the y value is plus, and now that's a negative, so I'll get rid of that and put that as a negative 1 over root 2. So this is going to be x minus 2 over root 2, which we could just simplify. X minus 2 is square root 2 squared. So there's 2 root 2's on top and 1 root 2 on the bottom. So we can simplify that as x minus root 2. Okay, so there is one tangent line that has a slope of 1 and it's tangent to the circle x squared plus y squared equal 1. So what we've done here, and this is the important point, the calculation is not necessarily the critical piece of it, but the point is that we're using an assumption about y, that it's implicitly, we don't know what that relationship is, but it's implicitly a function of x, and we sneak that into the equation here so that we have a function of x on the left-hand side now instead of a function of y and x. And when we take the derivative, we just have to keep remembering that y is a function of x, so we're going to have chain rules cropping up. And when we do that, that allows us to find the value of x and y at which the slope is equal to 1. All right, so I will wrap that up here, and we'll continue in a second video with more on the use of implicit differentiation.